All right. Uh, Hello, everyone. So again, in this video, we are going to discuss on how to plot the Thru-Fault current of the transformer under the category 2. In our previous video, we have already discussed on how to plot the Thru-Fault current of the transformer under the category 1. Okay, so again, we are using this guide, the IEEE standard C57.109/2018, which is the IEEE guide for liquid immersed transformers through fault current duration. Okay, so let's go to the page 11 of this guide. So it is the category transformer ratings. So previously, we have already plot the category 1. Now, we'll go to category 2. And for the capacity of these transformers for the single phase ranges from 501 to 1667 kVA. And for the three phase, 501 to 5000 kVA. Then, if you notice that the figure that we are going to use is the figure 2 and figure 3, but here in this video, we are going to use the figure 2. The figure 2, choose, okay, this is the figure 2. And if you, previously we have already plot this curve, which is the thermal damage curve of the transformer. And the values are already given in uh, table number 2 of this guide in page 12, which is the transformer short time thermal load capability. So if you notice that the at 2 seconds, the current times rated current is maximum. So these values we can already we can use this in plotting the thermal damage curve. And at the left side of this curve, we have this curve. It depends to the current is depends to the fault current of the transformers based on the impedances. So, and this current are only from 70% up to the 100% of the fault current of the transformer. So, we have here a curve so that we will discuss the what are the items or the points that we are going to determine. So here, this curve, it follows the I squared t, which is equal to k functions. And also this curve, so the area, it follows the same. But the k of each curve is different. Okay, so I will show you first on how to determine the k of each curve. So we have two number of curves, this one and another one. So we will determine on how to calculate the k. Okay. So first, determine the K of the thermal damage curve. So this is the thermal damage curve. So we will use this formula to determine the thermal damage curve. So here, since at 2 seconds, the times rated current is 25. Okay, so we have now the time and the current. So we can now substitute that. So at 2 seconds, the times rated current is maximum, which is equal to 25 per unit. So by substituting 25 squared multiplied by 2, so the K is equal to 1,250. So that is the K for this curve. Okay. How about this curve? This curve we can also calculate. So determine the K of the mechanical thermal damage curve. So at 2 seconds, again at 2 seconds, the fault current is maximum. So this is at 100%. 100% of the fault current. So at 100%, so the fault current of the transformer in per unit is 1 over the impedance. And substituting that here in the K, which is equal to I squared times T. So we have now the K, which is equal to 2 over the square of the impedance. Okay, let's go back here. So now, what are the other points? So we have to determine these 3 points. The point 1, or determine the coordinates, and the coordinates for at point 2 and at point 3. Okay. So at point 1, the time is already given and the current is maximum, which is at 100%. So at point 1, at 3 is equal to 2. The fault current is maximum. So in per unit, the fault current is 100 over the impedance. So the coordinate is 1 over z at 2 seconds. Okay. At point 2. At point 2, so we need to determine the time t. And this one, it is said that the fault current is at 70%. It is also in the guide. This curve is for the 70% up to 100% of the fault current. So this lines is at 70% of the fault current. So meaning the I at point 2 is 70%, and we need to determine the time TA. Okay. So at point 2, so time TA is unknown. And the fault current is at 70% of maximum. So meaning, as I have said, this is the 70% at maximum of maximum. So the fault current is 0.7 over the impedance. So this is the current. Then substituting uh, K, because they are in the same curve, right? The point 2 and point 1, so the K are the same. So the K, which is equal to 2 over the square of the impedance. So TA is equal to K over the square of the fault current. Then simplifying. Substituting this and also this. So z squared, also here you have to square this also. So this can be cancelled. So TA now is equal to 4.08 seconds. So this is at 4.08 seconds. Okay. Now at point 3, this is at point 3. Point 3 is within the curve of this thermal curve. So therefore, the K that we are using is the 1250, right? So point 3 time TB is unknown. This is the time TB, which is unknown, but the current is also at 70% of the fault current. Okay, so fault current is at 70%. So therefore, the current is 0.7 divided by the impedance. And okay, using again this value of formula where K is equal to 1 to 50. So TB is equal to 1 to 50 over the square of the fault current. So substituting it here, we have now the 1 to 50 over the square of the 70% of the fault current. And simplifying, so we have now the formula of the TB, which is equal to 251, uh, 200, 2,551 multiplied by the square of the impedance. So we can use this formula in determining the time and the current also. Okay, now, so let's have a sample problem. Let's say, for example, we have a 1,600 kVA with a 415 volts, three-phase, and the impedance is 5%. So plot the transformer Thru-Fault current curve. So since this 1,600 kVA is under the category 2, so we can apply this the formula or the points that we have derived. Okay, so first uh, calculate the full load current, which is the 1,600 divided by the square root of 3 and the 415 volts. So the full load current is 2,225 amperes. Now, let's go back to point 1. Since point 1 is already, the coordinates at point 1 is 1 over z at 2 seconds, which is the maximum or 100% fault current. So the fault current now, the actual fault current is 1 multiplied by the full load current divided by the impedance. The maximum or the 100% fault current is equal to 44,500 amperes at 2 seconds. And for point 2, at point 2, since we have already the time which is equal to 4.08 seconds, and the current is 0.7 over the impedance. So we can use that formula for the current in per unit, 0.7 over the impedance. So multiply that by the full load current divided by the impedance. So the fault current at 70% is 31,150 amperes at 4.08 seconds. Okay, so we have now the point 1 at point 2. Next, at point 3, since we have already derived the formula at point 3, so uh, substitute the impedance 2551 multiplied by the square of the impedance. So the time is 6.38 seconds. And the current at that point is also at 70% of the fault current of the transformer. So multiplying with the followed current divided by the impedance. So at 70%, the 31 fault current is 31,150 amperes at 6.38 seconds. So we have now the coordinates of this point 1, point 2, and point 3. Now, let's now prepare a table. This is the table from table 2. This value, they are already given, and also the times rated current. So we will apply it here in the table. So at 2 seconds, the actual current is 25 times the full load current. So 25 times multiplied by the full load current is equal to 55,625 amperes. And at 10 seconds, the times rated current is 11.3 multiplied by the full load current, which is equal to 25,143. And the same, and so to the other coordinates. Okay. So we have now this curve. This is called the thermal damage curve. And for the mechanical and thermal damage, or we call this as the frequent faults. So we have already here the at point 1, at point 2, and point 3. So at point 1, which is 2 seconds, and the current in per unit is maximum, which is 1 over the impedance, and the calculated actual maximum fault current is 44,500. And at point 4.08, the per unit is zero point 0.7 or 70% of the maximum fault current, which is equal to 31,150. The same here at point 3, the time is 6.38, and at point 7 or 70% also of the maximum fault current, which is equal to 31,150 amperes. So we have now this time and current characteristics for the thermal damage curve or infrequent faults, and also for the mechanical and thermal damage curve for the frequent or the frequent faults. So now let's have this in the Excel sheet. So this is the Excel sheet. And for the chart, if you want to know on how to prepare the chart, you can check the first video of this channel, and it is explained the on how to prepare in details. So I have already prepared this table. This is the infrequent faults or the thermal damage curve, and also the frequent faults or the mechanical damage curve. So we have the time and the current, and also for the frequent faults, the time and the current. Okay, now how to plot this time current characteristics. So just click the chart, right click, select data, click add. So the series name, let's say this is the thermal damage curve. And for the series X values, the X values are the uh, current. So just highlight this current. And the Y series values. The Y series values are the time. So just highlight the time. Okay. Now click OK and another OK. So we have now the thermal uh, damage curve. Next, how about the frequent faults or the thermal or mechanical damage curve? So again, click the chart, right click, select data, and click add. So series name, yes, it's a mechanical damage curve. And for the series X values, the X values are the current, and for the Y values are the time. Then click OK, another OK. So we have now the TCC curve of the 1600 kVA transformer. So we have the thermal damage curve and the mechanical damage curve. So that's all for this video. Thank you and God bless.